The objective of this topic is to be able to identify the principles of soldering, brazing, and braze welding.
Brazing and braze welding are processes which involve using non-ferrous filler metals to form a bond or union at temperatures above 840 degrees Fahrenheit, yet below the melting point of the base metal. Soldering, on the other hand, also uses non-ferrous filler metals to form a bond. However, the temperatures at which the filler metal becomes liquid is below 840 degrees Fahrenheit.
Brazing is the term used when the filler metal is distributed in a thin film between two or more tightly fitted pieces of base metal. The film thickness is usually between 1 and 3/1000ths of an inch thick, about the same as 2 sheets of paper. The brazing of a joint this thin depends on capillary action, the force by which a liquid in contact with a solid is distributed between the closely fitted surfaces of the joint to be brazed or soldered. We can demonstrate this with 2 pieces of glass, spaced about 1/1000th of an inch along one edge and about 10/1000ths inch along the opposite edge. If we dip the edges in colored ink, we see that the ink rises highly in a very thinly spaced area and only a smaller amount in the wider spaced area. When 2 pieces of cleaned and fluxed metal are placed tightly together and heated to the proper temperature, the filler metal will flow into the space just as the ink did.
Common types of joints used for brazing are lap, butt joints, and socket joints. The most common methods of heating to brazing temperatures are furnace, induction, flux bath, and torch.
With some furnace brazing processes, the parts are placed in a heated oven-like chamber with the filler metal and flux in place. The parts may be put in with conveyor belts or in batches on trays. Induction brazing uses an induction coil to heat the parts to the proper temperature. Flux bath brazing uses a heated molten salt bath to bring the parts up to temperature.
Of greatest interest to the welder is torch brazing. The process consists of cleaning the mating surfaces of the joint, coating them with flux, and placing them tightly together, and then adding the filler to the edge of the joint, allowing capillary action to draw the metal into the joint. Watching the behavior of the flux is the best way to determine when to add filler metal. First, the flux turns a milky color and starts to bubble as heat is applied. Just prior to adding filler metal, the flux will turn brown in color, indicating the cleaning action of the flux. At this time, the joint will accept the filler metal. The heat of the joint, rather than the flame, should melt the filler metal. If the temperature and the alignment are proper, the filler will spread over and into the joint. The filler should flow evenly, form a good bond, and melt at a temperature less than the melting temperature of the metals being joined. With proper preheating and fluxing, a workpiece can be brazed in any position.
Filler metals are made up of various combinations of copper, copper zinc, magnesium, aluminum silicon, copper phosphorus, gold, silver, and nickel. The flux, used to eliminate oxides and contaminants, are made up mainly of borax, boric acid, chlorides, and fluorides. They are formulated to suit the metals being joined and come as powders, as a paste, or as a liquid. Because of their composition, nearly all fluxes give off fumes that may be toxic, so they must always be used in well-ventilated spaces, and always keep your head out of the smoke and fumes. Fluxes are not needed in furnaces which have controlled atmospheres of inert gases, such as nitrogen, ammonia, carbon dioxide or monoxide, and so on. These inert gases take the place of the flux in preventing oxidation or contamination. Improper cleaning, insufficient flux, or poor joint fit-up will result in an inconsistent fill with a lack of flow into the joint.
Soldering is a welding process which joins 2 materials by heating them to the soldering temperature below 840 degrees Fahrenheit and then distributing a thin film of non-ferrous filler metal between the surfaces to form a bond. Like with brazing, the base metal is not melted with soldering. The filler metal is distributed by capillary action like brazing, except the temperature at which the filler metal becomes liquid is lower than brazing filler metal. The surfaces to be bonded must be clean in order for the filler metal to bond with the base metal. Flux is used with soldering in the same way it is with brazing, to assist with cleaning impurities and improve the wetting capabilities of the filler metal or solder. Once the base metal is properly cleaned and fluxed, heat is applied to the joint. This brings the workpiece temperature to above the melting point of the solder, but below 840 degrees Fahrenheit. Finally, the solder is applied by touching the filler rod to the workpiece. As the filler rod melts, the liquid filler metal flows into the joint by capillary action.
There are a number of different methods of soldering. Some are more common than others. One of the most common is the torch soldering of copper plumbing in residential homes. Soldering is used extensively in electronics, heating, plumbing, and manufacturing environments almost every day.
Braze welding looks similar to fusion welding, except that non-ferrous filler metal is used, and the base metal is not melted. Braze welding is similar to brazing, except there is no capillary action in braze welding.
Depending on the type and cleanliness of the base metals before braze welding, a procedure called tinning or pre-coating may need to be performed to facilitate a more rapid and uniform braze welded joint. Pre-coating of metals or alloys with tenacious oxide films such as aluminum, aluminum bronze, highly alloyed steel, and cast iron is almost always required to produce a sound braze welded joint. To tin the metal, the surfaces of the joint are cleaned by brushing or grinding. If they are ground, light filing and wire brushing is needed to remove any residue. Flux is added to the joint or applied to the brazing rod during the tinning operation. The metal must be preheated to open the pores of the material. Then the surface of the joint is coated with a thin film of filler metal. This ensures a strong bond between the braze weld and base metal. After tinning, the joint is then filled with as many passes as necessary.
Unlike brazing, braze welding is not recommended for out-of-position work, since this process does not use capillary action, and the highly fluid filler metal will simply run out of the joint. However, on small welds with close control, it is possible to braze weld in positions other than flat.
Brazing and braze welding offer certain advantages over other joining processes. For example, brazed joints can be disassembled at a later time, and brazing can be used to join dissimilar metals. Some common braze welding faults are too large a root opening, resulting in excessive root reinforcement; not enough heat, which causes a narrow, inconsistent braze weld with lack of bonding in spots; too much oxygen, which causes the weld to be depressed in the root opening; too fast a travel speed, which produces a narrow braze weld on the face side, is similar to a weld with insufficient heat. The visible white powder indicates the presence of oxidized zinc. This is an indication of too much heat on the braze weld joint.
The fumes from burned zinc oxide and from flux should not be inhaled, so remember, proper ventilation is always necessary with any brazing process. With care and practice, you should be able to produce quality braze welds.